Let's continue with our discussion of functional groups. So we're going to continue talking about types of compounds that contain oxygen. We looked at alcohols and ethers in the previous video, and in this one we're going to focus on what are called carbonyl compounds. So a compound that contains C double bond O is called a carbonyl compound. And so we have even more labels. We call the carbon in that double bond the carbonyl carbon. And the oxygen is called the carbonyl oxygen. So there's a number of different compounds, organic molecules, that contain carbonyl groups. To distinguish them from one another, to be able to put them into different classes, we look at what's directly attached to the carbonyl carbon. So we're looking at these attachments that I've just highlighted. So let's start by looking at a pair of types of compounds that are pretty closely related to one another, and those are called aldehydes and ketones. So we'll start with aldehydes. The abbreviated form of an aldehyde is RCHO. So let's draw that out. RCHO looks like this. So in an aldehyde, what's directly attached to the carbonyl carbon is going to be a hydrogen on one side, and then this R group could either be a carbon or a hydrogen. If it's a hydrogen, then what you have is formaldehyde, which we drew on the very first page of the notes. So this is formaldehyde. But we're getting to the point where we kind of want to bring in bond angles. So if we were to draw formaldehyde in such a way to reflect the bond angles, we would draw it more like this. And that's reflecting the fact that this is an sp2 hybridized carbon, and as such, there's a trigonal planar geometry surrounding it. And don't worry, we're going to review all of the hybridization states that we need, as well as the geometries associated with them, a little bit later in the course. So if you're not remembering this now, you could either go back and look at it. We're going to be going over it again. Let's draw some more aldehydes. There's another simple aldehyde. So notice on one side of the carbonyl you have a hydrogen, on the other side is a carbon group, so some alkyl group. This one is called acetaldehyde. And once again, that's a common name that you don't have to memorize. You don't have to memorize formaldehyde or acetaldehyde or the names of the compounds, the aldehyde examples shown to the right. Okay, so just the rules for naming things, but not these specific names that I'm giving you. So let's draw another one, because we can't get enough practice drawing structures. So when you study organic chemistry, they say you should always be doing so with a pencil in your hand. These days, I guess it would be either a pencil or a stylus, right? But the point is you need to be writing and drawing stuff as you learn the subject. This one's called benzaldehyde. And then shown to the right, vanillin and cinnamaldehyde. These are just two other examples of natural products that include the aldehyde functional group. Notice again, especially in the structure of vanillin, that there's other functional groups there as well. So see if you can pick those out. Let's think about ketones. Ketone is another example of a carbonyl compound. And in a ketone, the way that we distinguish a ketone from other carbonyl-containing compounds is that attached to the carbonyl carbon are two alkyl groups. So these attachments are both to carbons. So let's draw some ketones. Here's one that we've already drawn. This is acetone, which you've probably heard of, and that's a very common solvent. Here's a 4-carbon ketone. So we would imagine, because it has 4 carbons in its longest continuous carbon-carbon chain, that it would begin with bute, and we'd be right. This is called butanone. Let's draw a few more structures, again, just so that we can get the hang of this and get some practice drawing. This one is acetophenone. And then we've got a couple more examples that are printed over on the right-hand side of the screen. So the first one is called camphor, and that has a pretty unusual structure. So we have, what I've highlighted is a 6-membered ring, but then it also has another ring that's here. So we would call this a bicyclic compound. Or a bicyclic structure. And right here is the ketone functional group. That's also present in 2 places in progesterone, which is one of the human sex hormones. And remember, you identify the carbonyl group within your structure and then look at what's directly attached to the carbonyl carbon. In the case of progesterone, I'll just do one of the ketones. Each of these, upper right portion of the structure, each of those attachments is to a carbon atom. That makes that a ketone functional group. There's a whole bunch of other carbonyl compounds, and the next set include carboxylic acids, which we've seen already, but we're going to look at again, and what are called carboxylic acid derivatives. So first thing, to go back to the carboxylic acids, we looked at one when we were learning how to draw skeletal formulas. The general formula for a carboxylic acid is RCO2H. So all of them are going to include this grouping, CO2H. Remember, neutral oxygen, that is an oxygen that does not have a formal charge associated with it, has 2 bonds and 2 lone pairs. The R group here, R is typically a stand-in for an alkyl group, but it can be used in place of other things as well. This could be a carbon or a hydrogen. So let's draw some carboxylic acids. The simplest one would be the case where that is a hydrogen. So in a carboxylic acid, one of the attachments to the carbonyl carbon is a hydroxyl group. The other is going to be carbon or hydrogen. So if you have a hydroxyl group and a hydrogen, like in this structure, that's the simplest carboxylic acid you can imagine. This is called formic acid. So this is one of the components that makes an ant bite sting. So when they sting you and it hurts, it's because they're injecting formic acid into you, among other things. Acetic acid is a structure that we looked at previously. So here we're redrawing acetic acid. And back then I mentioned that you probably had seen this in a couple of contexts. So first of all, acetic acid, a 5% solution of acetic acid in water, is vinegar. So you've probably encountered it there if you've ever eaten salad dressing at any point in your life, which I'm assuming you probably have. The other place that you would have seen it is in Gen Chem 2, where it's a popular example to be used in calculations of pKa and Ka and percent ionization and these types of things. So I'm saying that that's kind of what we call a shot across the bow. A shot across the bow just means kind of a harbinger of something to come, a warning of something to come. Now, I don't want to put it in the context of warning, but I just want to put out there that, yes, we are going to be looking at acids and bases shortly, so you might want to start brushing the dust off of that as we go forward. Let's draw another carboxylic acid. This one you'll encounter a bunch. This is benzoic acid. So if you've ever eaten any junk food whatsoever, chips, soda, things like this, benzoic acid is probably in there along with its cousins and relatives, things that are based on benzoic acid. So these are all carboxylic acids. They all contain the same grouping of atoms, CO2H. So again, knowing these groupings of atoms helps you to know how to draw things. So if you know you have to draw a carboxylic acid, you know you're going to have that grouping of atoms in it. A carboxylic acid derivative is a compound that's going to produce a carboxylic acid when you react it with water. So a carboxylic acid derivative plus water in a reaction that's called hydrolysis results in a carboxylic acid. It's also going to result in a byproduct, but we won't worry about that. We'll do that next semester. So there's 4 that we want to think about. The first one is called an acid halide. So the structure of an acid halide is going to look like the following. It's going to have a carbonyl, and the carbonyl carbon is going to be attached to a halogen. And to a carbon. This one can't be hydrogen. That would create a structure that's actually kind of unstable, and so you'll never see something like that. It's always going to be a carbon group. So let me give you an example of that. Very, very common example that we'll be using a bunch in the second semester is this one. This is called acetyl chloride. So that's an example of an acid halide. The general structure of what's called an anhydride has 2 carbonyls. They're separated from one another by an oxygen. So this guy in the middle, we might call that the anhydride oxygen if you want. And the groupings on the ends, so let's just say R, these could be hydrogen or carbon. They can be the same or different. So let's look at a simple example of this. Again, one that we'll see a bunch of times in the second semester, and one that's very commonly used is this guy. This is acetic anhydride. A third carboxylic acid derivative is what's known as an ester. So an ester has a carbonyl that's flanked by 2 groups. So this R group over here can be carbon or hydrogen. Okay, so it could be either of those things, and this could still be an ester. However, the R group on the other side, so you have the carbonyl carbon, and then you have this oxygen on the right. That's called the ester oxygen. That's to distinguish it from the carbonyl oxygen, because you have 2 oxygens in the compound. The R group that's attached to the ester oxygen has to be carbon. So this has to be a carbon group. So it could be methyl, ethyl, a benzene ring, what have you, but it has to be a carbon atom that's directly attached to the ester oxygen. If this were a hydrogen, you'd have a carboxylic acid instead. So let's look at an example. Let's draw an example of an ester. Like so. This one's called ethyl acetate. And probably at some point, all of you have smelled ethyl acetate. It's a kind of a sweet, fruity smelling compound that's a component of nail polish remover. So it's one of the perfumes in nail polish remover, or one of the ingredients, if you will. Over here on the right, isoamyl acetate. This is another example of an ester. Now above we talked about formic acid as being one of the components that gets injected into you when an ant stings you or bites you. Isoamyl acetate has a couple of roles in our world, actually more than that, but two that come to mind. One of them, when a bee stings you, okay, so you've survived the ants, but now the bees are after you. When a bee stings you, it's injecting a little bit of isoamyl acetate into you. So this is a component of a bee sting. It's also one of the components that makes bananas smell like bananas. So this has a banana-y smell. So that makes me wonder, you know how when you get stung by a bee, sometimes that will attract other bees, maybe, I'm sure it's chemical signaling, pheromones, that kind of thing, but you have to wonder if it's because bees like bananas. I'm just kidding. Okay, the last kind of carboxylic acid derivative is called an amide. Now you look at this word and you think, well, there's a silent E at the end of that should be amide because that makes the I long. Not if you're an organic chemist. We have unusual ways of pronouncing certain words, and this is one of them. So this is an amide. So with an amide, you're going to have a carbonyl. And that's going to be flanked by two things. On the left side of the structure that I've just drawn, you have an R group, and in an amide, that R group can represent carbon or hydrogen. So that could be an H, or it could be something like a methyl group, or a benzene, or a cyclohexane ring, or a methyl group, or a butyl group, and so on. These other two R's that are attached to the nitrogen. So in an amide, you have a nitrogen directly attached to the carbonyl carbon. The other two R groups can also be either carbon or hydrogen. So let's draw an example of an amide. This is one that we're going to encounter later in the course. This is called DMF, which stands for dimethyl formamide. Now, amides are, as it turns out, components of the proteins in our bodies. So what we have, the structure over on the right, is what's known as a peptide, which is a chain of amino acids. So this was constructed by linking together various amino acids. The bond between the carbonyl oxygen and the nitrogen, in each case, so I'm drawing a little squiggly line across each of those bonds, is called a peptide bond or an amide bond. So these are peptide bonds, which are also known as amide bonds. So all three of those would have those labels. So those are the carbonyl-containing compounds. Now let's turn our attention to a couple of other types of compounds that contain heteroatoms. We'll start with nitrogen, and we're going to start with amines. So you might know already that if you have AM in the beginning of the name of something, it's probably going to have nitrogen in it. So ammonia, for example, amines, amides. In fact, the structures of amines are based on the structure of ammonia. So ammonia is NH3. The nitrogen has 3 bonds and 1 lone pair when it's neutral. So when I say that the structures of amines, which are organic compounds, are based on ammonia, that means that if instead of one or more of the hydrogens in ammonia, you have a carbon group, you now have an amine. So for example, CH3NH2. Instead of one of the hydrogens from ammonia, we have a methyl group. We would call this methylamine. you could have two of them. So this one would be dimethylamine. So you could have one alkyl group attached to the nitrogen, you could have two alkyl groups attached to the nitrogen, or three alkyl groups attached to the nitrogen. Those alkyl groups don't have to all be the same. You can have some that are same, some that are different. So there's all kinds of variation. We can classify amines based on how many carbons the nitrogen is bonded to. So based on how many carbons the nitrogen is directly bonded to. So it's slightly different than the way we classified sp3 carbons, alkyl halides, and alcohols. So let's look at examples. So I'm going to draw out three structures. And let me fix up this one so that it's not so horrifying. And there we go. All right, so from left to right. In the first example, the nitrogen is bonded to one carbon. That's a primary amine. And here's that guy right there that it's bonded to. In the second example, the nitrogen is bonded to two carbons. That is a secondary amine. And in the third example, I've highlighted the three carbons that the nitrogen is bonded to, which makes it a tertiary amine. So primary, secondary, and tertiary amines. A couple of other nitrogen-containing organic compounds. Nitriles. Nitriles have carbon-nitrogen triple bonds. So remember, nitrogen, when it's neutral, likes to have 3 bonds and a lone pair. Carbon likes to have 4 bonds. So make sure that you can see that that's the case in this structure. The R group in this formula must be carbon. It can't be hydrogen. Otherwise, we'd have HCN, which is hydrogen cyanide gas. Things would smell like almonds. We wouldn't feel so well, and then it would be over. Okay, so we don't want that. We're not going to be dealing with HCN. So this is a nitrile, an organic compound called a nitrile. The one that you're going to be seeing this semester is a solvent with this structure. This is called acetonitrile. And finally, to round out our discussion of organic compounds that have nitrogen that we need to think about at this point, nitro compounds. Nitro compounds include what's called the nitro group, which is NO2. So NO2 is known as a nitro group. And so let me draw an example for you that includes a benzene. So this is called nitrobenzene. Let's draw that again. Only this time what I'd like to do is expand the Lewis structure so that we can see what's going on in that group. Okay, so as you can see, the nitrogen has a formal positive charge and one of the oxygens has a formal negative charge. We're going to review how to assign formal charge shortly, but I wanted to show you the nitro group, all drawn out like that. And then let's extend this So remember that benzene with a methyl group on there is called toluene. You have toluene with 3 nitro groups attached in this way. This is TNT, which stands for trinitro toluene. Okay, so one more type of compound that we're going to be thinking about from time to time, functional groups containing sulfur. The one that we're interested in is called a thiol, also known as a mercaptan. So the abbreviated formula for this is RSH. So I'm going to give you one example. CH3SH. Now, sulfur is right below oxygen on the periodic table. And so its bonding and so on is going to look a lot like the bonding in oxygen. The only difference being because sulfur is farther down on the periodic table, it, unlike oxygen, has the ability to expand its valence shell. So it can have more than 8 electrons around it. Not something for us to worry about tremendously, but just throwing that out there, it's kind of a heads up. This one is called methane thiol. It's also known as methyl mercaptan. And this is the compound that they add in to natural gas so that you can tell if you have a gas leak, because natural gas by itself has no odor. So they put this in, and you probably already know that this is fairly foul smelling, so that if you have a gas leak, you detect this and you know right away that you need to call somebody. So a thiol is the sulfur version of an alcohol. So to make the comparison, the alcohol that's a methyl group with an OH is methanol, or methyl alcohol. So a very similar structure to the methane thiol.